So good. All right. Hey, John P. Sorry. Mr. Perez. Number 1 is yours, sir. Okay. It is. Very good. That is also correct. Now, can you talk to me a little bit about how you got that? Okay. So a little something like this, right? Okay. And turn this one on. Shut off the other ones I need for today. Okay, so you graph that. Looks like that. Okay, then what?
So what I do is I go to the table.
Okay.
I like to go to the table picture, scroll down.
Oh, poof, look, there's our first value. All the other ones are undefined, yeah.
So that's shape and it starts dating. That's our first day, actually starts right there.
Yeah, and it keeps going. So I will have values for 8 and everything after it. Yeah. You could also use your eyeballs in the graph. It's kind of hard to see because your graph creates a gap there, but or your calculator, rather, creates a graph there. But if I count the tick marks over 1, 2, 3, 4, 5, 6, 7, 8, I actually do get that first starting value there, and we see it's defined everywhere after. So that's how you write that. Some of my other students today, just to give you a little bit of background, I also did see this, and it's not wrong. You could say x is greater than or equal to 8 for the domain. They do mean the same thing. Thank you, John. That was good. I'm looking for Tessa. Yes, you're back. Okay. Number 2. This one, ooh. You're right. It's not a polynomial. This is a polynomial. So we know it's not a polynomial and it's not radical, so it has to be rational. So now we need to get to the root of why, Tessa, this gets categorized as a rational function. Do you know why? What visual characteristic kind of gives it away? The root word for rational is ratio. Ratio is fancy talk for fraction. So it looks like a big fraction, right? Poof, rational. Makes sense? Okay, did you have any luck with the domain? No. Okay, so I'll grab a new person. And it goes to Richard Fashion. I think you were just talking to me about this, weren't you? Oh, it's Chris. I knew it was like in here somewhere. Okay, let me tell you this. It is not what you did talk to me about polynomials, though. You were saying it was all real numbers. Those were the words that came out of your mouth, I think. I will go ahead and give you a hint. X has some restrictions on it. In other words, X cannot be any number under the sun. It cannot be any real number. There are 2 numbers that X is not allowed to be. And whenever I determine the domain of a rational function, my eyeballs go to the bottom. I'm never allowed to divide by, do you know, Rick? 0, yeah. So I look at the denominator, I'm like, well, what numbers would make that bottom equal 0? Do you know what they are? And? Yeah, very good. So right now we know that X cannot be 3, and it can't be -3. So now we go to our calculator again. And what you see is that where 3 is and -3 is, you have these walls in your graph, and you're actually not allowed to touch those points. So let's go to our calculator here. I'll show you what I'm talking about. So yeah, you press graph there. And what you get are 3 distinct pieces for this graph. So what we actually have to do is write our domain for each of those 3 chunks. Do you see the 3 chunks I'm talking about, Rick? So there's one over here. There's one in the middle. And then there's one over here on the right. Can you do any one of those? The domain. 3 pieces. I want to know if you can do one of the 3. So you're saying like -3 to positive infinity. So what you're saying is this graph starts at -3 and goes all the way over. But that's not quite true. Negative infinity to, yeah, that's the first part. Very good. Whoops, wrong slide. So it starts at negative infinity and head towards -3. And we get really close to -3, but we don't touch it because we're not allowed to. Then the graph picks up again in the middle. So what's the domain for the middle piece? You know, Chris. Yeah, -3 to +3. Very good. And then there's a piece on the right side of the graph. Does anybody know what the domain for that piece is? I hear whispering. Go ahead, John. Yeah, very good. It goes, oops, I wrote that wrong. Sorry. I think I said it and then I wrote it wrong. Sorry about that. There we go. So negative infinity to -3 takes a break, and then it's defined for -3 to 3. And then we get that other spot that our graph can't touch. And then it picks up again for 3 to positive infinity. Okay, questions about that one? Okay, last one. Brooke. No, not on part A. Because you are smart enough to use process of elimination. It's a polynomial. The domain for all polynomials is always the same, Brooke. I could put any number I want in for x, and I will get a y value back out. So the function is defined everywhere. So how do we say that? Yeah, great. There you go, kiddo. All right, questions about that? Our mission for today, to graph rational functions. I've worked really hard all semester to produce, everybody has their vocabulary copied, right? To produce a step-by-step process for a lot of the lessons that I teach. Today is very similar. That box that we're going to go to on the next slide here, that box lists everything you must have whenever you go to graph a rational function. But for starters, 2 of those elements are defined here. Vertical asymptote is a dashed vertical line that your graph gets very, very close to, it won't touch. It's directly correlated to zeros of the denominator of your function. Horizontal asymptote is a line, I should say, it is a line that your graph gets really close to at the ends. So as your graph heads towards positive infinity or negative infinity, the horizontal asymptote is just a line your graph gets close to there. It can pass through the horizontal asymptote. It's not like the vertical asymptote in that regard. Horizontal asymptote is more of a descriptor of what we call end behavior. Where does the graph go at its very end? So with that, there's 4 elements you're going to have to try to find. They may not always exist for every graph. That's what's tricky about these problems, is that they're all kind of different. Sometimes you'll have a vertical asymptote, sometimes you'll have x-intercepts, other times you won't. So you're going to work to find all 4 of these pieces, but not every graph will have them. That's why we practice. The first thing that we're always going to try to find is the x-intercepts, the places where the graph crosses the x-axis. This comes from just setting your numerator equal to 0, and then you solve. The y-intercept comes from letting x equal 0. The vertical asymptote, all you're going to do there is you're going to set the denominator of the polynomial equal to 0 and solve. And then the horizontal asymptote, that's the brand spanking new piece of information. That comes from a comparison that you're going to do. You're going to compare the degree of the numerator, or the highest exponent in the numerator, to the highest exponent in the denominator, and then make your horizontal asymptote from there. The last thing we usually do is we graph our equation in our calculator to go through and get a couple of points to make our graph nice and neat. So let's get started. The first thing that we always try to find for our graph are the x-intercepts. To do this, you set your numerator, that's the top, equal to 0. And I just wrote a statement that does not make sense. So here's that thing I was talking about. You're going to work to try to find the pieces, but you might not always have them. 1 can't be 0. That violates the one-to-oneness of our number line. So there are none. This graph does not cross at any point the x-axis. After the x-intercepts, do the y-intercepts. Oops. There will only ever be one, or else it's not a function. The y-intercept can be found old school. You just let x equal 0. So you let x equal 0. If you do that in this particular function, what you get is 1 over 0. And that's not defined. You can't divide by 0. So there's none. The next thing I work to find is that vertical asymptote that we defined a few moments ago. The vertical asymptote is a vertical line that your graph is not allowed to cross. To do it, you set your denominator, the bottom, equal to 0. So the bottom of this fraction is x. I set it equal to 0 and solve. Well, poof, that's done. So I have a vertical asymptote at x equals 0. I draw it in as a dashed line because ultimately it cannot be a solution point or set of solution points to our graph. So I draw it in dashed and then I label it. After I calculate the vertical asymptote, I calculate the horizontal asymptote. The horizontal asymptote is calculated by making a comparison. You must compare the degree of the numerator to the degree of the denominator. Everybody's like, what's the degree again? The degree is just the highest exponent that you see in the numerator. You compare it to the highest exponent you see in the denominator. So my function in this example is y equals 1 over x. I know that x is just raised to the first power. So the degree of the denominator is 1. The degree of the numerator, you might recall that we could attach x to the 0th power to 1, because anything raised to the power of 0 is 1. The degree of the numerator in this regard is then 0. So I need to now compare 0 to 1. 0 is less than 1. True story. Which means the degree of the numerator is less than the degree of our denominator. So we go back and we look at our checklist. And the case that we're focusing on right now is this guy right here, where the degree of the numerator is less than the degree of the denominator. Automatically, your horizontal asymptote is at y equals 0. So there's not even really any thought. It's kind of like a canned response. So our horizontal asymptote is at y equals 0. So you use your resources to kind of derive at that. Here's the equation for our horizontal asymptote, and then I draw it in. Y equals a number produces a horizontal line for us. I draw it in as dashed because it isn't actually a solution to the graph. So I've now gone through the checklist of 4 things I have to try to find each and every time. Now I go to my graphing calculator and I type it in. So my calculator here, go to my y equals, and you'll see that I have 1 over x already stored in here. So I press graph. There's my function. So I need that picture to appear on my coordinate plane. If you're unclear on the points, you could just do what Jonathan was referencing earlier. He likes to go to the table. Oops. And that is a completely viable option. So for instance, if you plug in 4, you're plotting the point 1/4 or 0.25. If you plug in 2, you're getting a half. If you plug in 3, you're plotting a third. You see how you can't plot 0? You get an error there? That's your vertical asymptote. That's a shortcut also for finding your vertical asymptote. If you look for where your y value is an error, that's the vertical asymptote. So you see that x can't be 0. So you grab some points off of your table of values or off of your graph, and you plot them. Oh, swing and a miss. Woo. Oh, kind of missed again. Fails the vertical line test. Darn smart board. But you get some points from your table of values and finish plotting the curve. Congratulations, that was the last bit of new material for your college algebra class. From here on out, it's just a little more of the same to get some practice, so let's do it. Questions on the process, because we're going to do the same thing until we get the hang of it and start to notice some patterns. All right, so in example 2, you are asked to graph the function y equals 2x squared over x squared minus 1. So what you're going to go ahead and do is start by trying to find your x-intercepts. And you always do this by setting your numerator equal to 0. If I solve this equation for x, I do so by dividing both sides by 2, square rooting both sides. X is 0, so this graph is going to contain the point 0, 0 as its x-intercept. To find the y-intercept, remember we let x equal 0. So I'm going to take my function, wherever I see an x, I'm going to put in a 0. You get 0 over negative 1, which again evaluates to be 0. So once again, we see that the point 0, 0 satisfies the equation. So we found the intercepts. Next, we worked on the asymptotes. Does anybody have any questions on how I found the intercepts? Good? Now the asymptote. So I always start with the vertical asymptote. You find the vertical asymptote again, or asymptotes. There could be more than one, as we've observed already today. I do this by just letting my denominator equal 0. And I'm just going to factor this because it's a difference of 2 perfect squares. So x equals negative 1 and 1. So I get 2 vertical asymptotes this time around. One is at 1. The other one's at negative 1. Two places your graph can't cross. So that's that. To establish the horizontal asymptote, you need to make a comparison between the degree of the numerator and the degree of the denominator. So this is me doing my horizontal asymptote. So I'm going to identify the degree of the numerator and make a comparison between the numerator and the degree of the denominator, or the degree of the numerator and the degree of the denominator, rather. Remember, the degree is the largest exponent. So if I look at my function, the largest exponent I see in the numerator is 2. The degree of the denominator, well, the largest exponent I see in the bottom of that fraction right there is also 2. So what I observe is that the degree of the numerator is the same as the degree of the denominator. So I go back and I look at my chart and I'm like, okay, well, the degree of the numerator is the same as the degree of the denominator here, which means that my horizontal asymptote can be found by just dividing the coefficients out in front. Remember, coefficient is just a number in front of a variable. So when I look at this one, I'm like, oh, well, the number out in front here is 2, and the number out in front is of the denominator is 1. So my horizontal asymptote can be found by making a ratio or a fraction with these two numbers. So my ratio is just 2 over 1, which is 2. So my horizontal asymptote for this problem is at y equals 2. We then take a moment now to go to our calculator and finish up the problem by throwing the equation into our calculator and then grabbing a few points. Let me press graph. Did I turn it on? I hope I did. Oh, I didn't. So you press graph, and there's my graph. So I now need to transfer these points onto my graph paper. And you can do that by going to your table. You'll see that my asymptotes are pretty apparent, so is my intercept there. But you're going to want to take these points, you could jot a couple of them down, and your mission is to take that general shape of the graph and transplant it onto your coordinate plane. So that's what we do. Finish out your curve there. Kind of looks like that. Questions about that? Ooh, what's up? Okay, I know exactly what you did. What is super important to remember, and I emphasized it and I forgot to mention it, yes, you have to quantify your numerator and your denominator always, or else it's gonna, what it did is it reduced out the x squareds for you, and it graphed 2 over -1. It graphed -2, which is why you got a line. So make sure you put your numerator and denominator in parentheses, that's important. Are there questions about that? Good? Okay, so the next problem, example 3, that is all yours. I wanted you to try one on your own for a little bit of independent practice. And then you'll see you have 3 more to do on your own for tonight. The last 3 in your notes are your homework tonight. So you're going to go ahead and get started on those for me today in class. Okay, after you finish those 3, remember that I'd like you to take another look at practice 7-7 tonight. You had the odd ones. If you lost your copy over the break, you help yourself to another copy. So please come in with that assignment for tomorrow. Ultimately, it's super important to recall that process. Those are some of the heavier point problems that are on your test on Friday. So you're going to want to keep that in mind, okay?